Hi, my name is Anirudh Chari, and I'm a junior at the Illinois Mathematics and Science Academy. Today, I want to share my project with you, Space-Time Conflict Spheres for Constrained Multi-Agent Motion Planning. You probably know that our roads today are pretty dangerous. In fact, 1.3 million people die in road accidents every year, and pedestrians and cyclists make up more than half of these deaths. A majority of traffic accidents are caused by human error. So in recent years, the development of autonomous vehicles has persisted in order to essentially remove human error by removing the human from the equation. Autonomous vehicles, while already statistically safer than current human-driven vehicles, are still far from perfect. Autonomous vehicles currently use perception-based systems for motion prediction. So if an autonomous vehicle, for example, sees another car that is driven by a human, it doesn't know that car's intention. It still has to predict where it's going to go, and with that prediction comes inherent uncertainty. So obviously we can get some pretty good predictions most of the time, but most of the time isn't good enough. So a potential solution that has emerged to this inherently flawed perception-based prediction has been connected autonomous vehicles, or CAVs. So CAVs essentially, instead of having to rely on perception to predict the motion of these other vehicles, they just communicate directly with the other vehicles. So if we have a system of connected autonomous vehicles, then they can directly communicate their current state and their intentions with each other, which means that they can coordinate with each other much more efficiently, which should mean that we have much safer transportation. So how do CAVs actually coordinate their motion with each other? Well, we can formulate this as what we call multi-agent motion planning, and we refer to each CAV as an agent. So there's been lots of work done in current years in multi-agent motion planning, mostly because of the high applicability to the CAV domain. Unfortunately, we still are not able to guarantee perfect safety in CAV coordination, which is largely why these systems have not been implemented yet. There exist two major issues in current work that limit current research's ability to be applicable to the CAV domain. First and foremost is discretization error. So in order to explain the problem of discretization error, we first need to understand what discretization is. So you should understand first that our real world is continuous time, which means that we can keep dividing time into infinitesimally small pieces. However, computers can't really grasp this whole fact of infinitesimally small numbers. So instead, what we do when we are trying to generate an algorithm, specifically a multi-agent motion planning algorithm, is we introduce a discretization. So for example, we might tell the computer that it only has to consider every 0.1 second time step. This means that it will plan and ensure that our solution is feasible at 1 second, 1.1 seconds, 1.2 seconds, 1.3 seconds, so on. However, this isn't always good because we know that our solution might be feasible at 1.2 seconds and 1.3 seconds, but we can't really conclude whether or not it's feasible at 1.25 seconds. So if there is a conflict at 1.25 seconds, then we wouldn't know. And this is clearly bad because if we decide that a solution is feasible in our discrete time domain and we can't transfer it to the continuous time domain, that means that we're unable to guarantee safety during actual operation. So this is clearly very bad, but a majority of work, because discretization is almost a necessity in multi-agent motion planning algorithms and generally planning algorithms itself, we're unable to evade discretization error, which really limits the applicability of current algorithms to the CAV domain. A second issue that heavily limits our applicability in current work is the inability to accommodate for dynamic obstacles. So a dynamic obstacle is just any moving obstacle. If you think about our roads today, you can see human-driven vehicles, pedestrians, cyclists, debris that may be in the road and moving around. Autonomous vehicles would have to consider all of these. And with connected autonomous vehicles, a majority of multi-agent motion planning algorithms actually entirely ignore the cases involving dynamic obstacles. Instead, they often make these very basic assumptions that our environment is either completely obstacle-free or that we are only dealing with basic static obstacles. So it seems like even with the current state of the art in CAV coordination, the same problem that we started out with is the problem that we're dealing with right now. Human drivers have the issue of not being able to deal with other human drivers and pedestrians efficiently. Autonomous vehicles have this problem, and now CAVs have the same problem because of their incompatibility with dynamic obstacles. But what if we were able to fix this? So I started thinking, how do we define a conflict between multiple agents? Well, a collision is going to occur when two vehicles are in the same place at the same time. So what if we just represent all the vehicles' trajectories in one central space-time grid? This would mean that intersections between trajectories would represent conflicts. And we can represent each trajectory as a capsule, which is simply a curve inflated with the radius of the agent. However, this is still a continuous time representation, which really still limits our flexibility. The key realization that I made is that a capsule is really just a chain of infinitely many spheres. Again, though, this notion of infinitely many is sort of hard for a computer to digest. So what we can do is discretize this representation into a chain of finitely many spheres. I spent a lot of time trying to figure out how many spheres we would exactly need in order to represent a trajectory. And upon figuring this out, I was able to essentially create a theoretical proof that said that if we scale the radius of each sphere in each trajectory by some magic number, and we're still able to find a solution, that means that the solution that we find must be feasible in continuous time. The reason that we're able to do this so much more simply than all the current algorithms which we consider state-of-the-art is that we're using spheres for our novel representation, and spheres have very simple geometry. This means that our trajectories that we generate are going to be very flexible. Space-time conflict spheres is the first CAV coordination algorithm with provably safe navigation among pedestrians and human-driven vehicles. In the future, I plan to continue building upon this method and exploring new optimization strategies and theoretical properties in order to maximize the impact of my work. After considering my work's implications more deeply, I began to realize the beauty and power of research. I often visualize innovation as developing in the same way in which a tree grows. Humankind over thousands of years has grown a tree of innovation, rooted from basic discoveries like fire and spanning to more modern innovations like the internet. Each successive branch grows from the previous work that facilitated it. And by performing research and making these novel discoveries, I would be helping to grow this tree, even if just with one little leaf. This contribution forms a foundation on which future research may be built. And over time, expansions within this tree will serve to advance the human condition. My goal in my life is to lead the movement of implementing perfectly safe autonomous transportation systems, as this is work that is both interesting to me and impactful for society. I'd like to thank my advisors from Carnegie Mellon University Robotics Institute, Dr. Changliao Liu and Mr. Roy Chen, for their extensive guidance throughout the research and writing processes. And finally, I'd like to thank the Davidson Institute for reviewing this application and providing me the opportunity to showcase my research. Thank you.